My name is Dan Boley. I'm in the Computer Science and Engineering Department. I'd like to talk about work that I've just started working on recently in the last few months. This has nothing to do with agriculture, so it's a change of pace. And instead of just taking the outputs of these deep learning models, I want to look at inside and try to understand why they come up with their predictions to make them more trustworthy. So this is using mechanistic interpretability which is used to expose conceptual structures inside artificial neural networks. So one idea we had was to try to apply this to a natural system that you can't disassemble explicitly, and namely the brain. So we have a data set of brain scans that came from the CMMR group, the magnetic imaging group here at the U. We have subjects inside an fMRI machine looking at natural scene images, and they're taking brain scans while they're looking at the images. And so then there exists some networks to try to disentangle these images to figure out what is the person looking at just by looking at their brain scans. So for example, you take an image, a yellow flag, and you pass it through this network, and it comes up with some features. And then the network tries to figure out what was the subject, person looking at. And our approach here is to use mechanistic interpretability methods or sparse autoencoders to try to disentangle the features in this image, in this brain scan. And this just gives you two examples. Looking at this yellow flag, you can disentangle, and one of the features that come up is just a yellowish feature. And another one is sort of rectangular flag feature. And there are a bunch of other features I don't have space to show. This is joint work with, these are my two students and some faculty in neuroscience. Brain scans a very limited data regime because it's very hard to get these brain scans. They only have 8 subjects in this whole data set. So some auxiliary projects we're working on is methods to try to augment the limited data regime. And one of them is if you're using diffusion models to try to, what we noted was that if you're at the noisy end of the diffusion model, then noisy images look like real, can't be distinguished from clean images if you already have a certain level of noise. So you could use those to augment the data that's used to train it. And a second approach is in reinforcement learning, which is another data sparse model system, is to look at try to generate an LLM that would synthesize data that looks like the real data, and you need a discriminator or predict to filter out the ones that don't, and use that as a way of augmenting the data.